Uh, Welcome back to the week three's discussion session. So today, what we'll do is we'll begin by actually, clarifying a doubt uh, of the assignment, and then I will formally put forward, you know, the agenda for this discussion session. But so there was a doubt in in one of the questions of assignment two. I guess it is question 8 of assignment 2, and there was some clarification that needs to be made, although it has been already posted in the discussion forum, but nevertheless I'll also like to clarify it here. So the question is simple. We have just solved these kind of things multiple times in the previous weeks. So what the question stated is that there was a rectangular slab and its left face, let's say I call it as 1, this, and the right hand face I'll call it as 2. The left face is exposed to temperature. So if I correctly remember, the temperature at which the left face uh, is exposed to is equal to 400 Kelvin, if I correctly remember the values. And on the right hand face, the temperature was equal to 600 Kelvin. Okay. And it was given that the thermal conductivity of the material is equal to, I think it was 100. I think so. Yeah. So K was given to be equal to 100 watt per meter Kelvin. That was the thermal conductivity of the material. And it says that the thickness of this material, that is the length, uh, is given to be equal to 100 mm. Okay. In that context, it's a simple question. They just ask us to evaluate what will be the heat flux uh, in this scenario. Okay. So first and foremost, we need to understand that, so there is something which is known as the direction of heat transfer that we have repeatedly discussed in the last class. And the direction of heat transfer is always from point or a node, you can say, which is at the higher temperature, to a node which is at the lower temperature, which means in this case, whatever be the coordinate system you choose, the direction of heat transfer will always be from the right hand side of the slab to the left hand side of the slab, typically because it is just given to you that this face is exposed to a temperature of 600 Kelvin and this face is exposed to a temperature which is less than 600 Kelvin. So given this statement, you can make you can at least conclude in this scenario that your rate of heat transfer will be from right hand side of the face to the left hand side of the face. Okay. uh, to the left side basically. Now you can argue that if there is some cooling that is going on, then there can be some flux which will get dissipated to the other side. That is fine, but in this scenario, since nothing is given, we are just assuming that heat transfer will take place from this face to the other face, which is the left face. That is from the right face to the left face. In that context, if you calculate now, your heat flux, will basically be equal to, so first of all, you need to need to understand how to apply the Fourier's law here. Okay, so Fourier's law will tell you that your flux is equal to minus k of dt dx, but this form of Fourier's law tells you that since dt dx is in the direction of decreasing temperature, that's why in order to make the flux positive, there is a minus sign here. But in this scenario, you already know that your flux is going to be in the negative x direction, so you can say that your q prime or q double prime is going to be minus k is given to be equal to 100, which is watt per meter Kelvin, times, here you already know that your flux is going to be in the minus x, so you can write that your temperature difference is just 600 minus 400. This just says that your flux is indeed going to be equal to negative, and this negative sign says that you are now choosing a coordinate system which may be something like this, where you have chosen your positive x to be in this direction. So this is important when you use. So one thing that you need to realize, that when you use the Fourier's law, defining the coordinate system is also very important. Okay, and based on this coordinate system, this is what the Fourier's law gives us, in particular the sign that I am considering. Okay, I hope you have understood my point. If not, I repeat once again. So this is in general the application. I mean, this is in general the Fourier's law that we apply whenever there is 1D heat transfer and your thermal conductivity is constant. But you might now ask me that in this case, we have generally encountered scenarios where the heat flux is generally positive. Okay, but that form is made in order to, give you the magnitude of the heat flux so as to, say that, okay, this much is the quantity of flux that is being transferred. But in order to understand the essence of the direction, you first need to, choose a coordinate axis and then see that what will be the direction of the heat flux based on the fact that rate of heat transfer or the flux will always be in the direction from the phase which is at a higher temperature to the phase which is at a lower temperature. So based on this coordinate axis and from the fact that your right hand side of the phase is at a higher temperature, the direction of flux will now always be in the negative x direction. Okay, and that's the reason why your flux will come out to be equal to negative. uh, in magnitude it's always positive, but this negative signs is essentially telling you that it is in the direction of negative x direction. That's it. Okay, so and your dx, it is 0.1. So if you calculate this, I think this would be what, this would be minus of 200 times 100 divided by 0.1. So I think this would be 200 kilowatt per meter square. So it is minus 200 kilowatt per meter square, which means that your Q prime is 200 kilowatt per meter square in the negative x direction. Okay, so this is what the answer should be. Yes, I understand there's a mistake in the problem, because in the problem and in the solution that they have provided, I think they have mistakenly calculated the temperature gradient instead of calculating the heat flux. That's why in the unit I think they have written it Kelvin per meter, which is actually wrong if you want to calculate heat flux, because we all know that the unit of flux is watt per meter square or kilowatt per meter square. Okay, so I think that's a mistake in the question. This question is under scrutiny and it will eventually be changed, and you will be given marks for I mean everyone will be given marks for this particular question, that is question number 8 of assignment 2. Okay, I hope this is clear now, and I once again thank you for participating in the discussion forum, and please keep posting there, and yeah, that's it. Okay, so I hope this is clear. So if this is clear today, so now we are in a point of discussing what we are going to see today, and this is based on the uh, video lectures of week 3 to be precise, and the contents that we will discuss today is going to help you in solving assignment 3 in particular of the assignments. And what we will discuss today is something which is known as conduction resistance network, and we will discuss this resistance network analysis for slabs and cylinders, typically for, or in other words, for Cartesian and cylindrical coordinate systems. Okay, Cartesians when we will be dealing with slabs, cylindrical coordinate systems when we will be dealing with heat transfer in hollow cylinders or in a solid cylinder or things like that. Okay, so that's the agenda for today. Before formally moving on to it, uh, I'll stop here again as we do for a couple of minutes, just for you to set yourself ready, and then we will start off with the discussions. All right. So as you have as you can see from your screen, we will now be discussing something which I feel is a very important and a uh, critical, I would say, an aspect which require understanding in terms of conduction heat transfer is the resistance network. Okay, so we will be discussing this in details. Although you have seen the, the theory that is associated with this resistance network in your lecture series of week 3. However, I'll just give you a quick recap of what the things were that you already saw in your this week's lecture series. But uh, at the same time, we will solve some problems associated with this resistance network. Okay, so if you remember, if I now consider a plane slab as we have been doing in these, in these weeks, so I say that this slab, you know, you can understand that that's this slab. So it's, so first of all, the assumptions that we considered will hold good. That is, we'll be considering 1D heat transfer. These assumptions will hold good uh, here also, and we'll consider steady state. Okay, in that context, you have seen that, let's say if there is a phase which is maintained at a temperature T1, okay, and the other phase which is maintained, let's say, at a temperature T2, okay, you can effectively write the rate of heat transfer. Let's say I tell you that T1 is greater than T2. Then if I ask you uh, what is the rate of heat transfer that takes place from the left hand side, we all know that the direction of heat transfer or the heat flux will be now from the left hand side to the right hand side, because the left face is at a higher temperature. But if I ask you what will be the rate of heat transfer, you you then need to ask me one question. First of all, is there is heat generation that is taking place inside the slab? That is one aspect that should come to your mind. The second thing, if there is no heat generation, then you know that your heat flux is going to be constant, because we are considering constant properties as well. We'll consider that material properties are constant. And we'll also consider there is no heat generation inside the slab. In that context, you know that your heat flux is going to be constant, or you know that your temperature profile T as a function of x, where I can tell that my x direction is in this direction, that is, the plus x is from the left to the right, is what conventionally we use. And you can tell that the temperature profile, which will now be just a function of x, is going to be linear. Okay, so in that context, you know that if you need to calculate what is the heat flux or the rate of heat transfer, the first and foremost thing that we have seen, that we can use the heat diffusion equation. But there is an easier way, or a more effective way, I would say, of calculating the rate of heat transfer given this assumptions whole considering these assumptions into the picture, is by using something which is known as resistance analysis. So what we do is, we choose two nodes, and these nodes typically represent the temperature nodes, and then kind of draw a resistance that would arise when the flux, you can say that when the flux moves from the left hand, or the heat energy moves from the left hand side of the phase to the right hand side of the phase. Okay, so drawing analogy from the electrical network, or the electrical the electrical circuits that you might have studied in your elementary, +2, or initial classes of your bachelors. You can say that the temperature difference is analogous to the voltage difference in case of electrical networks, and your flux that you write, this is analogous to your current. Okay, in that context, you can now say that we can define a resistance in between these temperature nodes, and we know that the direction of heat flux will be from the direction of higher temperature to the phase which is exposed at a lower temperature. Now the question is, this resistance, as you know, for cylindrical slabs typically come out to be L by Ka. Okay, where L is this length, K is the thermal conductivity of the slab, you all know, and A is basically the cross-sectional area that is perpendicular to the direction of heat transfer, which is just this area. Is basically this area. Okay, so this L by Ka that you saw, I guess you have derived this in your theory classes. This is very easy to derive, but this L by Ka, this is known as conduction resistance for rectangular slabs. Okay, this is very easy to derive. That is typically because you can show that your heat flux is going to be a constant quantity, and then multiply it with the area. You can then find out the rate of heat transfer, and then take all the quantities that is that is outside, that is associated with your delta T to the denominator, and you can effectively write that as you can basically write that as a voltage difference by resistance, and that's typically gives birth of this resistance network. Okay, this you have already seen in your theory classes, so we'll not go this typically just becomes a repetition, so we'll not discuss more into this, but this is the idea. As I was telling you, this L by Ka becomes your conduction resistance. So in that context, you can now tell that your heat transfer, which we denote it as Q, which is nothing but the rate of heat transfer, is going to be, or I think we use small q for this, I don't remember, just check it out. So this rate of heat transfer is nothing but now the temperature difference, which is delta T, divided by your RTH of conduction, and this RTH of conduction is what we call it as the conduction resistance for this rectangular slab. We will denote it as RTH of conduction, and this just gives you, the rate of heat transfer. Okay, where you know that your RTH of conduction is just L upon Ka for rectangular geometries. Okay, now let's look into a more realistic case of this resistance network. Is that now if I have this is something, I believe this is something that you have already seen in your theory classes. Now if I have, let's say I have a slab which is the same old slab that we have been using. That's the left face, that's the right face. The left face is exposed to T1. The left face is exposed to T1, the right face is exposed to T2. Now I tell you that there is an insulation that is being provided at the left face. Okay, meaning that there won't be any heat flux along the left face, and whatever will be the heat flux, that will be in this direction. That's one way of saying it. Okay, and in the right face, what you are doing is you are cooling the right face, okay, by providing some ambient air, or you can call it as cool air, which is flowing at a temperature T infinity, and they bear a heat transfer coefficient H infinity. So I hope the system of interest is clear. So we have a rectangular slab. Okay, you just consider 1D heat generation. That is always valid. 1D heat transfer. Sorry, there is no heat generation here. It's just 1D heat transfer. Constant properties. Okay, and the left hand side of the slab is insulated. But what you are now doing is you are cooling the right hand side of the slab by providing cool air, which is at a temperature T infinity with a heat transfer coefficient H infinity. Okay, and the thermal conductivity of the slab is equal to K. In that context, now if you draw the resistance network, your resistance network will be, so this is your temperature node T1. Then we all know there will be a conduction resistance that we already saw. That is due to conduction heat transfer taking place within the slab, and this we all know is L by Ka. Okay, and this node temperature is going to be T2, but this does not finish the resistance network, because when the heat energy reaches this right hand side of the slab, it will now see that okay, there is a cool air that is being flowing, onto which I can now dissipate the energy. Okay, and that's the reason why we will have one more resistance into the picture. and the final temperature node will be T infinity. Now this resistance, that the extra resistance that I have drawn, this is known as your RTH of convection, okay, and this is known as the name suggests, this is known as resistance due to convection. And we have seen in your class that your RTH of convection is equal to 1 upon H infinity times the A, where you know that your A is again the area that is perpendicular to the direction of heat transfer, okay, which is basically this area that I am talking about. Okay, I hope this is clear. Again, you need to understand that for doing this resistance analysis, there is no heat generation that is taking place, and and of course, heat 1D heat transfer, that's fine, constant properties, and no heat generation. Yeah. So then, okay, so then if you now ask me what will be the rate of heat transfer, which we call it as Q, this then becomes T1 minus T infinity divided by summation of all the resistances that is there in the resistance network. Okay. So now there will be two resistances which will be T1 minus T2 divided by the conduction resistance, which is L by Ka, plus the extra resistance that come into the picture due to convection, which we call it as RTH of convection, and this is just 1 upon H infinity times A. And if you guys have a closer look, this 1 by HA or 1 by H infinity, H infinity times A, this comes from the Newton's law of cooling itself, because we know that the rate of heat transfer due to convection is HA times delta T. So you bring this to the denominator, then it becomes delta T divided by 1 upon HA, and this is typically the rate of heat transfer due to convection. Okay, and that's how it becomes the convection resistance, which takes the form 1 by HA. Okay, so this is how we use the resistance network. The beauty of the resistance network is that, see, if I now have this complicated scenario like this, if you ask me, given this assumptions that we considered, if you ask me what is the rate of heat transfer, I will ask you two things only. One, the extreme temperatures of the nodes, okay, which is T1 and T infinity, okay, which is basically this. I don't even need to know what is the temperature of this phase. That is a plus point that comes into the picture when you use the resistance network. I will just ask you what is the temperature of the right phase from which you are starting the resistance network, and the temperature of the ambient air, which is at T infinity. And then all I require are material properties. For instance, I will ask you what is the value of K, what is the value of the heat transfer coefficient, that typically we need this value, and the dimension, of course, the area that is associated with this, and the length, of course, which is this length. Okay, so given the temperature at the extreme nodes, and you know the material properties along with the dimensions of the material of interest, you can evaluate what will be the resistance, what will be the rate of heat transfer for using resistance network. And this is where and this is why I said that this is one of the most powerful thing of when we study conduction heat transfer in particular, because we can write the rates of heat transfer or the heat flux. So if you divide this by area, for instance, if you divide this by area, then you will get your heat flux. So your heat flux is basically Q by A, and then it will be just T1 minus T infinity by L by K plus 1 by H infinity. Okay, so it is just Q divided by area. So you can calculate the rate of heat transfer or the flux just by knowing the material properties and the dimension and the temperatures at the extreme nodes of your resistance network. Okay, and that's the reason why this method is useful. Now remember, although what I want to say is, if I now have a geometry, let's say a cylinder, the convection resistance will always be equal to 1 by HA, because that comes from the Newton's law of cooling. But this L by Ka that we wrote here, this is sensitive. This resistance, that is the conduction resistance, is sensitive to whatever material that you are I mean, what is to, so it's sensitive to the shape of the material. For instance, what I want to say is, if I now have a cylinder, let's say a hollow cylinder, okay, and heat is being dissipated from the inner face to the outer face in the radial direction. Then if you ask me what is the conduction resistance in this case, then in that case it is not equal to L by K. In that case, as we will see later on, it is equal to ln of the, it is equal to natural log of the outer radius by inner radius divided by, I think it's 2 pi L. I think that's we will see that very shortly. I mean, but it is not equal to L by K. Okay, so that's so it's actually ln of R naught by Ri divided by 2 pi K. That becomes the conduction resistance in case of cylindrical geometries, but we will see that later on. But it is not equal to L by K, that is, it is not equal to this form that we use in case of rectangular slabs, meaning that your shape of the geometry will dictate what will be your conduction resistance. For instance, if it's a sphere, your conduction resistance will then be different. It is then going to be 1 by 4 pi K times Ri minus R naught. It is something like that, if I remember that correctly. But it is going to be different. And you can derive all those things from, the basic heat diffusion equations. As you have already saw a glimpse in the lecture classes. Okay. So that's the idea. So what we saw is, so just for a recap, what we saw is like we saw the rate of heat transfer for a single slab that is exposed to temperatures T1 and T2, and then writing the conduction resistance for that case. And then we saw a scenario where one face was insulated and the right hand side of the face is exposed to a ambient air which is at heat transfer coefficient H infinity, which bears a heat transfer coefficient H infinity and a temperature T infinity. And then effectively we wrote what will be the rate of heat transfer for that case. Okay, in terms of the resistances that are involved. Okay, all right. So I think that's the background that we require to solve the problems. I'll stop here for a couple of minutes and I'll display the first problem on your screen. You can have a look and then we will try to solve this using the concept of resistant network analysis. Okay, so what this problem says is, let's have a look at this problem. It says that in a manufacturing process, a transparent film is being bonded to a substrate as shown in the sketch. Means that there is a film which is transparent. You can call it as a, so you can consider it as a liquid film that is bonded to a substrate. Okay, in this form that you can see from the screen, from on your screen. Okay, now whenever you do a bonding, I mean, you guys might have studied in typical manufacturing courses. You need to provide heat at the interface. Okay, that is typically done to strengthen the bond. Okay, so in this scenario also, to strengthen or to cure the bond at the temperature T naught, a radiant source is used to provide a heat flux Q naught double prime, all of which is absorbed at the bond interface. So what they are saying is that in order to strengthen the bond, which is this, which is at the interface of the film and the substrate, you are providing a heat source in the form of a heat flux on this interface. Okay, and this heat source, whatever you are providing, this gets absorbed at the interface, meaning that there is no loss of energy taking place. Okay, how much? So if you can think of it like you are using a resistance heater to basically provide energy on this interface, and whatever energy that you are providing, it is not getting dissipated or it is not getting lost. It is, so whatever your energy that you are providing, it is, all of it is being absorbed at the interface of the film and the substrate, is what the question is telling us. Okay, the back of the substrate is maintained at a temperature T1. This is given, that is the lower half of the substrate or the back of the substrate, it is maintained at temperature T1, while the free surface of the film is exposed to air at T infinity and a convection heat transfer coefficient H. That is, the free surface of the film, which is basically this surface, it is exposed to air having, temperature T infinity with a heat transfer coefficient H. Given this, and given that given that the thermal conductivity of your substrate is 0.05, the thermal conductivity of the film is 0.25, this length LF of the film is 25, that is the thickness of the film, the thickness of the substrate is 1 mm. That's all given to you. What they're asking us is that first of all you need to show the resistance circuit representing this steady state scenario of this system. Okay, and then what they're asking is, given that your T infinity is 20 degrees Celsius, that is the temperature of the ambient air, your heat transfer coefficient to be 50, the lower half of the substrate to be at 30 degrees Celsius, you need to calculate the value of Q naught double prime. That is how much of energy is basically required to, strengthen this bond, is what the question is asking us. Okay. So that's so that's what they're asking. I'll first of all I will highlight the important parameters of interest. They are saying that, so one of the important things that you need to understand, that all of the heat that you are providing, it is getting absorbed at the bonded surface. Okay, then the temperature of this lower half of the substrate or the back of the substrate, it is at 30 degrees Celsius. Okay, and T infinity is at 20 degrees Celsius. Okay, then of course the thermal conductivity of the film, this is given to be equal to 0.05 watt per meter Kelvin. The thermal conductivity of the substrate is given as 0.05, sorry, the film is 0.025, the substrate is 0.05 watt per meter Kelvin, and the individual lengths are given as LF and LS, where your LF is equal to 0.25 mm and your LS is 1 mm. Okay, these are the values that they are given. So given this, let's try to draw the resistance network for this configuration. And of course, this temperature, you can call that the temperature at which the interface of the film and the substrate is to be T naught. Okay, so given this information and the explanations that I have provided, let's now try to draw the resistance network for the system. Okay, so now in order to draw the resistance network, we must first think from where do we start. Now in the earlier cases, the simpler cases where there was just one slab and it was exposed to ambient, it was easy to understand that, we can start it from the node which is at a higher temperature, okay, to the node which is at a lower temperature, which is just from the left hand side of the face to the right hand side. But here you must understand that the portion of the system which will be at the highest temperature is not the film that is exposed to air, and it is not the back end of the substrate, but it is the interface actually which is at temperature T naught. And that is obvious, right? Because you are providing heat at the interface. So first of all, the node where there will be the maximum heat, or the maximum energy, will be the interface which is at a temperature T naught, or it is the bond which strengthens the film and the substrate. So we will start off by writing the node which is at the highest temperature, which is T naught. Okay, that is the interface of the film and the substrate. So in resistance network, it is more customary, you can draw it in whatever form you want, or in whatever way you like, until and unless it is correct, but it is customary to start off from the node which is at a higher temperature, which is at the highest temperature of the system considered. Okay, and in this scenario, as I have explained, since you are providing heat at the interface of the film and the substrate, I will start the resistance network by drawing the T naught node, which is the interface temperature of the bond and the substrate. Okay, now you need to understand that once you are giving energy to this interface, what will this heat energy do? It will try to be dissipated in the either directions, right? Because the energy can move so your rate of heat transfer can take place in this direction, your rate of heat transfer can take place in the other direction as well. So let's say I'm considering that some of the energy will get dissipated from the upper side of the flame to the cooling air. Okay, so then I can say that one part of the energy will be going to the upper side, which we'll considering as the left hand side of this resistance diagram. And remember, when this goes, it will encounter a conduction resistance just because of this stationary film. We will call it as RTH of conduction F, which will denote the film. And let's say for the sake of simplicity, we will call it as RF, which is the conduction resistance of the film. But remember, this is not done because the energy upon reaching the top surface of the film will see that there is a cool air that is being flowing at the temperature T infinity, which you can consider it to be at a to be at a lesser temperature than the nodal temperature of this of then the nodal temperature that is present at the interface of the film and the air, meaning that there will be a further heat dissipation from the interface of the film to the surrounding air. Okay, and this is where you will get another resistance, that is which will be the convection resistance of this system, and we will call it as R convection, CONV. Okay, so this is your RF, which is the conduction resistance of the film, and this is your convection resistance that exists between the interface of the film and the that exists due to the temperature difference between the interface of the film and the ambient air. Okay, and finally this temperature node is going to be T infinity. Okay, now since there is a node that is present, let's name this node. Let's since there is this node present, let's name this node as the temperature at the interface of the film and the flowing air as, let's say, T2. Okay, and then this becomes equal to T2. But this does not finish the resistance network, right? Because we have only considered that the energy that is going to be dissipated from in the plus x direction. Okay, but there is also some energy that will get dissipated in this direction, right? Because whenever you are providing heat, it will see that, okay, I can move in the forward direction, I can also move in the reverse direction, I mean in the downward direction as well. So then the resistance that will come into the picture because of the presence of the substrate alone will be the conduction resistance of the substrate, and I will denote it as RS. Okay, and then there will be this nodal temperature T1, which is just T1, which is nothing but the temperature at the back of the substrate. Okay, and this is just T1. So this somewhat finishes the resistance network, but we are still not done yet because we have not shown the flux that is providing heat at the interface of the film and the substrate. That is, there should be a flux that is Q naught double prime, which is providing energy at this interface, and from that there is a dissipation of energy on the top side and on the bottom side as shown by this resistance network. Okay, so meaning that there will be a flux now. Okay, Q, let's say I'll call it as Q2 double prime and Q1 double prime, where you can now interpret that Q naught double prime is the energy that is being provided at the bond surface, that is at the interface of the film and the substrate, and because you are providing energy, heat will try to dissipate. Some part of it is being dissipated in this direction, that is towards the top hand side of the system, which is denoted by the flux Q2, and some part of it will get dissipated from the right hand side, which is Q1, from the bottom surface of the substrate, which we are denoted as by heat flux, which is Q1 double prime. Okay, so this finishes or this completes the resistance network of the system. Okay, so this is your resistance network of the problem. Okay, and you have answered the part A of this question, in which they have asked you to just show the thermal circuit representing the steady state heat transfer situation. Okay, And this is indeed your Fermat circuit for this problem. Now in the second problem, they have asked you, given that all these quantities are known, that is your T infinity, your H, okay, that is the heat transfer coefficient, your temperature T1, and all these material properties and the lengths, you need to calculate the magnitude of this heat flux that is being provided at the interface of the film and the substrate, okay. And that is what is your part B of the problem, okay. So part B is to evaluate Q naught double prime. Okay, now how do we do that is what we will try to understand, okay. So you can think of it like at the interface of the film and the substrate, whatever the energy that is coming in form of the flux Q naught double prime is going to be dissipated into these two fluxes. That means if you apply a energy balance, that is if you apply energy balance at node T0, that means at the node which contains the temperature T0, you can simply write, that is just by energy conservation, that your flux which is coming in, which is Q naught, is going to be your Q1 double prime plus Q2 double prime, okay. Now this is obvious, right? Because if you minutely consider a control volume which just encompasses the interface, the energy that is coming into the interface is this Q naught, and the energy that will be going out from this interface, from the minute control volume or from the differential control volume, is just Q1 plus Q2. And that's what we are writing. We are just using the steady state energy balance principle, that is Q in, that is energy in. So what we are doing is we are just writing energy in terms of the flux, that is energy per unit area, per unit time, of course, and this is equal to E dot double prime. This is equal to E dot double prime out. That's what we are basically writing. Okay, just simple energy balance that we have used it in the previous class. Now we need to calculate this Q naught double prime and because of that we should be in a position to evaluate these quantities Q1 double prime and Q2 double prime, and this is where the resistance network will be of our help. Okay, so what I can now write is, remember this Q1 double prime. So what is Q1 double prime? It is the flux that has left this node T naught, which is moving in the right hand side direction of this resistance network. Okay, meaning that your Q1 double prime is simply going to be your T naught minus the temperature of this node T1 divided by the resistance, which is nothing but the conduction resistance of the substrate, which is just Rs. Okay, this is your quantity Q1. In the same spirit, if you evaluate Q2, Q2 is going to be using the concept of resistance network, and if you remember the case 2 that we discussed today, Q2 is going to be the temperature difference between T naught and T infinity, which is T naught minus T infinity, divided by all the resistances that exist between these two temperature nodes, which is nothing but the resistance of the film and the convection resistance that is being provided by the flowing air. Okay, so this Q2 double prime is going to be T naught minus T infinity divided by Rf, which is the conduction resistance of the film, and Rconv, which is the convection resistance. Okay, now the good thing is all these quantities are known to us, which is sufficient for us to evaluate this Q naught double prime. How is that? So it's just formulas that we just need to use now. So Rs, as we all know, this is the conduction resistance. So I'm just writing this is the conduction resistance offered by the substrate, and this is going to be the length of the substrate Ls divided by the thermal conductivity of the substrate. We will not consider the area because we are only interested in flux. So the area is just going to be your rate of heat transfer divided by A, which will just give you the flux. Okay, and that's the reason why we will not consider the area. Okay, so this is going to be your Rs, which is the conduction resistance offered by the substrate. And then your RF, that is the conduction resistance, offered by the film per unit area is simply going to be LF by KF. Okay, but remember there is one more resistance, that is the convection resistance, and we know that this R convection, which is the convection resistance offered by the flowing air, is 1 upon h times, it's just 1 upon h, because again the area will be just cancelling out because we are considering flux, which now means that I know these three quantities and I can just substitute because all these temperatures are known. So then your Q naught double prime, if you substitute all the values, you can, so your T naught is at 60, your T1 is at 30, okay, and then this is going to be your RS, which is just LS by KS, and then this is going to be your 60 minus T infinity is at 20 divided by LF by KF plus 1 upon H. Okay, and if you substitute these values, because you know that your LS is your LS is 1 mm, your LF is 0.25 mm, your individual thermal conductivities are known, your heat transfer coefficient is also given. Your heat transfer coefficient is given to be what? It is given to be 50 watt per meter square, that is your H is going to be 50 watt per meter square Kelvin. Okay, which means if you substitute all these values, you should get the answer. I have already calculated that. You should get the answer to be 2833 watt per meter square. All you need to do is just substitute the values in SI unit in terms of this, in place of these like variables. That's it. So if you do that, you should get your heat flux, which needs to be provided at the interface of the substrate and the film, to be as 2833 watt per meter square. Okay, that this much amount of energy is required for this given system. Okay, all right. That's the first problem that that I wish to discuss, and that this is it. I'll stop here for a couple of minutes. I'll let you guys, try to grasp this problem. And how did we solve this? How did we write the resistances? And more importantly, see the main crucial thing. Oops, sorry. The most crucial thing of this problem is drawing this resistance network, and trying to apply the energy balance on this node, and then writing these fluxes in terms of the temperature difference between the nodes and the resistances that arises in between the considered nodes. Okay, that's all that's the idea that you need to develop if you want to solve, if for you to solve these kind of problems. Okay, all right. Now we will solve a more interesting and a more realistic problem in as a second problem, and that is trying to understand the heat transfer loss that takes place from the aeroplane windows. And this is something that I have already said you by giving a glimpse of it in the first week, and we will now learn by taking actual information, actual flight information and flight data. We'll try to now learn that why airplane windows need to be designed in a specific way, rather than, I mean, specific way meaning that there are two glass panes and in between there is just stagnant air, and why this needs to be done. I mean, this is one of the reasons why this needs to be done. There are also something pressure losses and all those things that come into the picture. So that is a separate, that is a mechanical perspective. But the one perspective is minimizing the rate of heat loss from the space inside the aircraft to the surrounding, which is at a much lower temperature than the than the inner space. Okay, so we'll solve this problem. We'll try to understand that why these kind of configurations are essential uh, in designing airplane windows by taking real flight information and data, and then building and using the resistance network, of course, into our advantage, and then try to find out what will be the heat loss that will take place in some cases. Okay, or in a case if we want to make a different design, or a design where there is just the glass pane, and then the space between the two glass panes is just between the glass pane is just exposed to the aircraft body and the ambient air. Okay, so we'll solve this problem, and I hope you like this problem because it's kind of a realistic problem. uh, but before that, I will again stop here for some time. I'll just come in 2 minutes by filling a glass of water, and in the meanwhile you can look back into the previous problem, and also you can think of how to solve this second problem. Okay, I'll just come in 1 minute. Okay, sorry for the interruption. So, so as I said, we will try to figure out that why this kind of configuration of airplane windows are essential for minimizing the heat loss. So for that, what we'll do is we'll try to compare two cases. One, when there is just single glass pane that is present in between, the temperatures in between, the body of the aircraft, that is inside the aircraft, and the ambient temperature. Okay, and what we'll do is, for simplicity, we will ignore the convection resistances that will come into the picture, meaning that, let's say, this is the space inside the body of the aircraft, and this is the space that is ambient. Okay, that is basically the surrounding of the aircraft. We will say that the temperature inside the aircraft, that is the temperature of the space inside the aircraft, is the temperature that will be that so this is the temperature that will also be the face of the glass pane, is something that we will assume, meaning that the convection resistance between the interface of the glass pane and the ambient air is neglected for the sake of simplicity. But in general, there will also be a convection resistance that will arise in this scenario. But again, I repeat, for the sake of simplicity, I am assuming that the left hand side of the glass pane, which is in contact with the with the body of the aircraft, inside the aircraft, is just the temperature T1, which is, let's say, the comfort air conditioning temperature of which is the comfort air conditioning temperature inside the body of the aircraft. That is the temperature of the glass pane that is exposed uh, in that side. On the in the same spirit, the temperature of the ambient air, which generally is of the order of minus 40 degrees Celsius, and typically, let's say, it is minus 46 degrees Celsius, is the temperature of the glass pane that is exposed to the ambient. Basically, this is just a simplified model that I'm establishing just for you to appreciate the just for you to appreciate the importance of using the resistance network analysis. Okay, in this context, you can you can add a convection resistance into this picture, but just to keep things simplified, I have neglected that case. Okay, and we'll consider a second case, where there are two glass panes, and and in between these two glass panes, okay, there is an air space uh, which is present, and you know that the thermal conductivity of air is 0.24 watt per meter Kelvin. Okay, that means now this is the phase that is exposed to the inside body so it is the phase that is exposed to the inside body of the aircraft, and this is the phase that is exposed to the surrounding of the aircraft, and these are the two glass panes. Okay, which is the preferred consideration, which is the preferred configuration that you can see, because in this picture you can see that there is a glass pane here, there is a small gap, okay, which is filled with air, as you can see, and there is another glass pane that is in the exterior of this window. So this is the second configuration that is typically used in in aircraft, and we will prove that the second configuration is much beneficial in terms of minimizing the heat loss, and the first configuration is not desirable. Okay, and this we will do by using the concept of resistance network. Okay, now for some information that I want to provide, so this picture is a picture of a, I guess it's a picture of a Boeing 787 series aircraft, and the altitude at which this kind of airplane flies is roughly around 40,000 feet, which is of the order of 12,000 meter. The outside air temperature, that is the temperature of the ambient, is minus 46 degrees Celsius. You can understand how cool it is at this altitude. And the inside air temperature, where the human beings sit basically, that is inside the body of the aircraft, is 21 degrees Celsius. So you can interpret that this T1 is 21 degrees Celsius, that is the inside body of the aircraft. Again, I repeat, the convection resistances are neglected, meaning that the glass pane, the left hand side of the glass pane, is exposed to 21 degrees Celsius temperature only. The right hand side of the glass pane, which is exposed to the atmosphere, is now at minus 46 degrees Celsius, because the airplane is flying at this or cruising at this altitude, and typically this is the cruising altitudes of all long haul flights typically, and that's why this is at a minus 46 degrees Celsius. And yeah, in the second case also, it's just the same configuration. This phase is just at 21 degrees Celsius, and this phase is at minus 46 degrees Celsius. But the difference only lies is that now, instead of using a single glass pane, I have used two glass panes separated by a air space, and this kind of configuration is called sandwiching configuration. It's like two glass panes are sandwiched by a air space, which is filled with just stagnant air. That's it. Okay, so our objective, so what is the objective then? Our objective is that, given this scenario, we will try to calculate the rate of heat transfer for case 1, and we'll try to calculate the rate of heat transfer for case 2. Okay, that's what we are trying to do, and that is what the question is asking. They're asking what is the heat loss in both the scenarios. Okay, and which design, of course, is preferable, and we will prove that the second design is much preferable than the first scenario. Okay, so let's do it. Let's do it for case 1. So the case 1 is simple, right? Because in case 1, I just have a glass pane, okay, having thermal conductivity Kg, and this length is, let's say, Lg. And this phase is at temperature T1, this phase is at temperature T2. So the rate of heat transfer Q, or let's say small q, for case 1 will be denoted as 1, is just going to be T1 minus T2 divided by Lg by Kg times A. Okay, so what you can do is, I'll keep this length as a variable. I will keep this length as a variable, that is this length Lg, and I'll call it as 4 times L. Okay, where L is the length of this glass pane. So it is the length of one single glass pane of of the second scenario, that is the length of this single glass pane is L. So that means this length is also L, because these two glass panes are identical. That is what I'm saying. So this length, I'm saying that this length is going to be 4 times L. Okay, is what so I'll not put a value to this L. I'll just keep it as a variable. Okay, so in that context, your Q1 is just going to be T1 minus T2 divided by Lg, which is just going to be 4L by Kg times A. Okay, let's call it as equation 1, because we are simply going to compare the ratios of Q1 and Q2, and we will see we'll then analyze that in which case the rate of heat transfer is higher. Okay, all right, so in second case, let's see the second case, which is more interesting and which is actually desirable, is that I have now two glass panes, okay, of individual thicknesses L, and this is L. Okay, and then I have air. Let's take this length, okay, to be twice L, such that the summation of all these lengths becomes equal to the length of the single glass pane. I mean, that's something that we are doing for the ease of calculation. That's it. Which means in the second case, if I draw the resistance network, okay, the first resistance will be because of this glass pane, which is just going to be L by Kg times A. The second resistance is because of the air, and that will become twice L by K air times A, and the third resistance will be L by Kg times A. Which means if I write the rate of heat transfer for the second scenario, it is going to be the delta T, which is T1 minus T2, this is T1 and this is T2, divided by the first resistance, which is going to be L by Kg times A, which is the resistance offered by the glass pane. And remember, there are two glass panes, so this resistance is also going to be L by Kg times A. So that's why we'll multiply this by 2. Plus there is an air resistance, which is twice L by K times A. So this is just going to be twice L by Ka times A. Okay, that's your second equation. It's nothing else. We are just using the fact that your rate of heat transfer is delta T divided by the summation of resistances. Okay. Now, let's do one thing. So what I will do is, I will try to, okay, I will try to, so let's do this. Let us divide Q1 by Q2. Okay. So if I do this, what do I get? I get T1 minus T2 divided by 4L by Kg times A. Okay. And then I have T1 minus T2 divided by what? Twice L by Kg times A plus twice L by K times A. So the good thing is, I can cut these two temperatures. Okay, these areas will also get cancelled. This length will also get cancelled because this is just L. Which means, what do I have? I have which means I have what? I have Q1 is going to be Q1 by Q2, and then this will go as 2 by Kg plus 2 by Ka and then this is going to be 4 by kg. Okay, now let's substitute the values. I know that my kg is going to be, so what is kg? Kg is the thermal conductivity of glass, and it is of the order of 1.4 watt per meter Kelvin. The thermal conductivity of air is going to be 0. So what was that? I think that's 0.024. Yeah, 0.024 watt per meter Kelvin. So if you just substitute the values, it will be what? It will be Q1 by Q2, and then this is going to be 2 divided by kg, which is 1.4, plus 2 divided by k, 0.024. Okay, and then this is going to be 4 by kg, which is 1.4. Okay, so if you calculate so let's do the calculation. Let's see how much do we get. Okay, I don't have a calculator with me. Okay, so I don't have a calculator with me right now, and I don't have the results for this as well. This is just a frame problem that I just framed it from my mind. So what you can see is that you can appreciate that this quantity, that is the numerator. Let's say I call it as, let's say what? Let's say I call it as alpha, and alpha is known, right? Because this quantity is, you just need to calculate this quantity. And let's say I call it as beta. So you can appreciate that this alpha is going to be much greater than beta, which means that my Q1 is going to be much greater than Q2. Okay, and this means that the Q1, which is, see, this is going to be greater because you can see that there is this 2 by 0.024. So this quantity will be much greater than 1, which means that this overall quantity will be dominating than this quantity. Okay, and that's the reason why I said alpha is going to be very much greater than beta, because of this. Typically it is because of this quantity. Okay, 0.024, that is 2 by 0.024. Okay, and then you can see that because of the fact that this alpha is going to be very much greater than beta, where alpha beta are some known constants, that is, just evaluate this quantity and that is just equal to alpha. Okay, what I am trying to say is that since this numerator is very much greater than the denominator, you can say that your Q1 is going to be much greater than Q2, which now means that the rate of heat transfer in the case where there was just a single glass pane of length 4L, okay, and if this glass pane is now replaced by two individual glass panes of length L and L, okay, and in the space in between this glass pane, there it is sandwiched by a space of still air, your rate of heat transfer significantly decreases to Q2. Okay, that means the second configuration, in which there are two glass panes instead of using a single glass pane of length 4L, if there are two glass panes of individual length L, and if there is air in between these two glass panes, the heat loss that will take place from the body of the aircraft to the ambient air is going to be very much less than the heat loss that would take place in the otherwise scenario where there is just a single glass pane. Okay, and this is typically the reason why this configuration is preferred. The second configuration is the preferred configuration. This is the preferred configuration for airplanes, and that is the reason why you see this configuration in all the airplane windows. Okay, now the next time you visit or you board an airplane, you see that you will see a glass window, okay, basically like this, and then there will be an airspace in between, and then you will see the exterior window, which is basically here. Okay, so that is typically one of the reasons why the designing of the airplane window is in this manner, in order to minimize the rate of heat loss that will take place from inside the aircraft to the you know to the surrounding, which is at a much lower temperature. You can see that the surrounding is at a minus 46 degree. Surrounding is at a temperature of around minus 46 degrees. Okay, now the point is, why are we trying to minimize the heat loss? See, the reason is very simple, because the air conditioning, the amount of air conditioning power that is required to maintain this temperature, at 21 degrees Celsius, that is the comfort level of humans. This power comes from the gas turbine engines that are actually below these wings of the airplane. That is typically the engines that you see in aircraft. Okay, so it is that Brayton cycle, or it is that Brayton cycle power that these engines generate, and the power of that is so the majority of the power that the engines of an airplane generate is used to create thrust, which basically drives the, which basically lifts the airplane in the sky. Okay, but in the same case, in the same scenario, when let's say the majority of the power that the gas turbine engines of an aircraft generates is for the thrust, but some part of it is used for air conditioning as well. Now we cannot say, or it's like, if the heat loss is very high, then in order to maintain the inside temperature of the aircraft at 21 degrees Celsius, you need enormous amount of power. Okay, because the heat loss, because there is significant heat loss taking place from inside the aircraft to the ambient. Okay, now since that chunk of heat loss is significant, in order to maintain your temperature at 21 degrees Celsius, you need enormous power, meaning that now the turbines need to generate even more power. Now that is not desirable, right? Because you want, because first of all, you want the airplane to be lightweight, meaning that you cannot use a very heavy engine. Your engines also need to be light, and in the same context, you also need much of the power that the engine generates in order to create lift. Okay, so it is just only a small portion of the power that is used for utilizing and that is used for air conditioning, uh, uh, that is used for air conditioning requirement inside the aircraft body, and that is typically the reason why you want to minimize the heat loss such that the air conditioning requirement is lower, and the power consumption is lower, and the size of the engine aspects and the lift that will create it, that all those things, can be enhanced. That's typically the idea why you require you require to minimize the heat loss that takes place from inside the body of the aircraft to the surrounding air of an aircraft. Okay, all right, so I'll again stop here for some time. I hope you you understood this problem and you like this problem. This is more of a real world problem that we were looking at. Uh, and yeah, okay. If there are any doubts, you can report. Also, please feel free to clarify your doubts in uh, in the discussion forum of the course as well. And yes, that's the thing. Okay, so we will now look into another aspect of resistance network, that is resistance network for cylindrical objects. Okay, so just like in slabs where your resistance was just equal to L by Ka, now what we'll do is we'll consider cylindrical systems. Like, I consider a hollow cylinder of this form, let's say a heat pipe kind of thing. Okay, so what I now say is that this is a hollow cylinder. As you can see, I call this direction as my Z direction. Maybe you can then say that this direction is your R, which is the radius of the cylinder, and then moving around this Z axis becomes your polar angle theta. Okay, now I say to you that this cylinder, which is a hollow cylinder, the inner face of the cylinder, okay, I say that this is at a temperature T1, the outer face of the cylinder, this is at a temperature T2, and I tell you that the inner radius is equal to Ri, while the outer radius is equal to R2, and the length of the cylinder of interest, I call it as L. Okay, and then in this context, if I ask you that what is the rate of heat transfer due to conduction only that will take place from the inner surface of the cylinder maintained at temperature T1 to the outer surface of the cylinder that will be at temperature that is at temperature T2. Of course, you can interpret from this problem that since the problem is axisymmetric and the cylinder is assumed to be infinitely long, which renders the fact that your direction of heat transfer is just going to be in the r direction from it is first. So number one, it is going to be radially outward from the inner surface to the outer surface, because I'm assuming the fact that your T1 is greater than T2. So this is what is going to be the direction of heat transfer, okay, in the radial direction. Okay, so heat transfer in r direction. Meaning that your 1D assumption is still valid here. Your 1D heat transfer is still valid. I am assuming constant properties, that is, material properties are constant. Okay, and again I am assuming that there is no heat generation. So in that context, I hope you have seen the derivation in the class. In that context, you can write your rate of heat transfer as, let's say, small q to be T1 minus T2. This is again going to be RTH of conduction, but now this RTH of conduction is not going to be L by Ka, because this is no longer a Cartesian geometry. This is a cylindrical geometry. So this is going to be ln of the outer radius R0 by Ri divided by twice of pi of K times L, where K is the thermal conductivity of the cylinder material and L is the length of the cylinder. Okay, so this is known as, so this resistance that you wrote, this is known as conduction resistance. This is known as conduction resistance for cylindrical geometries. Okay, and this aspect of analyzing heat transfer in cylindrical geometries is even more useful, typically because most of the pipes and stuffs like that are important for heat transfer are of cylindrical shape, to be precise. Okay, and that's the reason why analyzing this in cylindrical coordinates is of useful, is useful, and the reason behind is related to its application, because most of the pipe because like most of the things that are used for transferring heat and let's say heat pipes and all, they are of cylindrical shape, uh, to be precise. So now at least you know what is the resistance due to conduction. It is just ln of r0 by ri divided by 2 pi kl. So there is one more useful concept, that is, you can now assume that there is a flow of air that is being taking place from, let's say, the outer surface of the outer surface of the cylinder. I call it as, let's say, H infinity, which is the heat transfer coefficient of the ambient air, and let's say this is the heat transfer coefficient, so sorry, and the temperature of the ambient air is T infinity. So this means that the air is flowing at H infinity and T infinity from, this is from the outer surface of the cylinder. Okay, that means you are cooling the cylinder again by using a using a cool air, using cool air which is at temperature T infinity with a heat transfer coefficient H infinity. And you can also assume that you can also consider that there is a hot fluid, that is flowing through this pipe, okay, which bears a heat transfer coefficient HO and a temperature TO. Okay, now in that case, if you want to write the rate of heat transfer that will take place from this hot fluid to the ambient air, you can then extend this analogy. I mean, you can then say that your Q, and I hope you can now realize that there will be two extra resistance that will come into the picture in terms of convection resistance, and that Q is now going to be T0 minus T infinity, that is the extreme temperature nodes, that is this T naught and T infinity, okay, divided by the resistance. So the first resistance is going to be 1 by HO times AO, I would call. That is the area of this surface, okay. Then there is going to be the conduction resistance because of the cylinder, which is going to be ln of R naught by Ri divided by 2 pi KL, okay. And then there is going to be one more convection resistance, which is going to be the resistance offered by the ambient air, which is going to be 1 by H infinity times A infinity, where A infinity is the area of the exterior cylinder that is available for heat transfer, okay. So that's the two other resistance that comes into the picture if you consider airflow and a liquid flow, a hot liquid flowing at a heat transfer coefficient H naught, and there is a cooling air uh, that is after the interface of the outer cylinder, which is flowing at the H naught uh, and with temperature T infinity. Okay, and I hope you can now draw the resistance network as well. This is simple now. This network, so the node, this is going to be T naught, which is the maximum temperature node, and then this resistance is going to be 1 upon H naught A naught. This is going to be ln of R naught by Ri divided by 2 pi KL. And then there is going to be one more resistance, which is 1 by H infinity times A infinity, and then this is going to be your T infinity. And from here you can calculate the rate of heat transfer as delta T divided by summation of resistances. Okay. So this is one more aspect, that what happens when there is convection taking place in cylindrical shapes. And this is a case of more useful scenario because that is what heat pipes are designed for. Okay. So what they do is they basically try to transfer the heat from the hot or the cold object, vice versa. It's like it's just the same thing. For instance, if T naught is greater than T infinity, then your heat transfer will take place in this direction. In the other case, it will take place in the opposite direction if if your temperature of this fluid is greater than the temperature of the fluid that is flowing inside the cylinder. Okay, but in any other, in practical applications, this is what they do basically. In order to transfer heat from one fluid to the other fluid, they place a pipe which is generally of very high thermal conductivity because you want the resistance to be minimum. Because see, if your thermal conductivity is very high, you know that your conduction resistance will be less, because if this term is high, this overall term is going to decrease. So that's how they kind of transfer heat. That's how heat transfer take place in heat exchangers typically. Okay, they place heat pipes of this form, and then they allow the heat to take place by conduction in between the material of the heat pipe. And also there are convection resistances that will come because of the ambient fluids and the fluid that is flowing inside the tube. Okay, and this is how uh, people and this is how heat pipes operates typically. Okay, but there is one more thing that I wish to discuss, and then we'll call it a day in cylindrical geometries. And I think you have also seen that this is something known as critical radius of insulation. So what happens is, this is something that you need to understand a little bit. So let's say once again I consider a pipe of some inner radius and outer radius. Okay, it's a pipe. So let's say this inner radius is R1, the outer radius is R2, and I can say that the inner surface, which is basically this surface, this is at some temperature T1, and the outer surface is at some temperature T2. And I say that my T1 is greater than T2, which means that my direction of heat transfer is just going to be radially outward. Now, there is something which is known as insulation or an insulating material. So what people do is they put another a concentric kind of material, which is the insulating material, as like, so there is another material that they would put, okay, of some radius which is of course greater. So let's say I call it as R3, which is of course greater than R2 and R1. And then they try to see that putting this material, okay, in addition to this material, will the heat transfer increase or decrease? Now there is a common myth that adding insulation to to cylindrical objects, let's say, always decreases the heat transfer, but that is not the case. Okay, that is typically because although I'll not explain the theory in detail because this is already done, the reason behind this is because if you plot the rate of heat transfer and on the x-axis if you plot the thickness of insulation, and the thickness of insulation is typically denoted as T, and this is just R3 minus R2. That's it. That is, this is the thickness of insulation. Okay, this is precisely the thickness of insulation T. So if you plot this T versus Q, you can see that your so the curve is basically something like this. Okay, that means if you add insulation, you go on adding insulation up to a certain distance, your rate of heat transfer will decrease, and after that your rate of heat transfer will basically increase. So the minima on which, so it is that thickness at which the rate of heat transfer is minimum, this is known as RCR, which is the critical thickness of insulation. And this RCR is known as the critical thickness of insulation. So you can see that you go on adding your insulating material, that is you go on, so you increase the thickness of insulation up to a certain point. Okay, if you reach a certain point, at which your rate of heat transfer will be minimum, and that certain point is known as RCR, which is the critical thickness of insulation. Now you have derived it in your theory classes, is that your RCR for your cylindrical shape, so RCR for cylindrical geometries is going to be is just K of the insulating material by the heat transfer of the ambient fluid. So it is just K by H naught or K by H infinity. Okay, this is that. So this you can derive. This is for your cylindrical shapes. Okay, for spherical shape, you can show that it is 2K insulating material by H naught. So it is 2K by H naught to be precise, or H infinity. Okay, but the important thing is what happens if you further keep on increasing the thickness greater than the critical thickness of insulation. So if you then increase the thickness beyond this point, your rate of heat transfer actually increases, and this will keep on increasing. Okay, and you can tell that this point, if you just draw a horizontal on this point, then this thickness, let's say I call it as T1, this value of T1, this is known as crossover radius. So this is called crossover radius because you add you add insulating material of this much thickness. This is as good as telling that, so this will produce the, so this will transmit heat as good as without any thickness of insulation basically. Okay, because these two rates are just the same. That means you add a material of thickness T1 and you calculate the rate of heat transfer. You don't add any insulating material and calculate the rate of heat transfer. Your rates will exactly be the same. Okay, but beyond this rate, so beyond T greater than T1, okay, so beyond this T greater than T1, okay, your rate of heat transfer actually increases when you add an insulating material, which breaks the myth that insulation always minimizes the rate of heat transfer. In fact, to be precise, if you add material greater than, so if your T is greater than RCR, okay, your rate of heat transfer anyway will increase, as you can see from this curve. Okay, now the reason behind this, so you can ask me now, and you should ask that why is this curve like this, why it is not like this, or why it is not just monotonous. Okay, the reason behind is because of the fact that when you keep on increasing your thickness of insulation, okay, your conduction resistance increases but your convection resistance decreases. So you can show that your conduction resistance, so the resistance plot is something like this. Okay, so the resistance, so if you plot the resistance RTH, which is a cumulative effect of the conduction and the convection resistance, your resistance plot is actually something like this. At RCR, your resistance is actually maximum. After RCR, your convection resistance dominates over the conduction resistance. It's like your resistance, your cumulative effect of the resistance will decrease beyond RCR, and that is the reason why your rate of heat transfer increases after you cross the critical radius of insulation. Okay, because there are now two resistances that will come into the picture. One, the convection resistance, because we know that the convection resistance, our convection, this will be of the order of 1 by area of the outer area of the outer surface. So I'll call it as A naught. And your conduction resistance, R conduction, it will be proportional. So it will be of the order of ln of R naught by Ri. Okay. And this A naught, I can write it as 1 by 2 pi R naught times L. So this is again of the order of 1 by R naught. Okay. So you can see that your R of convection is of the order of 1 by R naught, while your R of conduction is of the order of ln of R naught by Ri. Ri is, so if you consider Ri to be constant, it is of the order of ln of R naught, which means when you increase R naught, your convection resistance actually decreases, your convection resistance actually decreases, your conduction resistance actually increases. So that's the reason why you get this shape of the resistance, and that's the reason why you get this shape of the rate of heat transfer. Okay, so beyond T greater than RCR, your resistance decreases because your convection resistance dominates over the conduction resistance. Okay, because you can see that your convection resistance is proportional to 1 by R naught, your conduction resistance is proportional to ln of R naught by Ri. Okay, and since your convection resistance dominates beyond T greater than R naught, your overall resistance actually decreases because this R naught actually increases when you keep on adding insulation. And typically that's the reason why your rate of heat transfer actually increases when you increase thickness of the insulating material greater than your critical thickness of insulation. Okay, and that is the reason why we see a minima in the rate of heat transfer, and that minima you can basically, so that the minima is easy to evaluate. Okay, you calculate the net resistance, which is just going to be R convection plus R conduction. You differentiate this R with respect to T and set this equals to 0. You will simply get this to be equal to K insulating by H infinity. That's an easy exercise that you can do, and you can then show that this minima, because that's how you calculate minimas of curve, right? So you can show that this minima is going to be K by H naught for a cylindrical geometry. Okay, so that's the idea behind heat transfer in cylindrical geometries, and how this critical thickness of insulation works, why there is a minima, and what happens to the resistance, why the curve is like that, is something that you need to understand here. Okay, similar analogy you can do at your end. You can do the same analogy for spherical geometry, and you can show that your RCRs for your spherical geometry will come out to be equal to K by H, 2K by H to be precise. Okay, but the important thing is, think about, this critical radius of insulation is not valid for Cartesian systems. Okay, you cannot find a critical radius of insulation for a Cartesian slab or for a rectangular slab or things like that. Okay, all right, so I think we have done a few good discussions today. This ends the discussion of this live session. I hope you have learned it. So just for a recap, what we did is, like, we started off, so first of all, we looked into a problem of the assignment. We clarified the doubt. That was question number 8 of assignment 2, where, so basically we were required to just calculate the flux, and that's what the flux we got. And then we looked into the resistance analysis of heat transfer. We looked into the conduction resistance. We then looked into the conduction resistance and the convection resistance combined, and what will be the total heat transfer. Okay, and then we solve the problem where we use the fact that how do we draw the resistance analysis and the resistance network, how do we do the resistance analysis by first drawing the resistance network, and then using the energy balance principle, we calculated the heat that is required at this interface, just by using the simple energy balance and by using the help of the resistance network, of course. Okay, and then we solved a realistic problem, and we looked into the case that why in airplanes, in aircraft, this kind of configuration in the windows are desirable, rather than using a single glass pane. Why there is a sandwiching glass pane with airspace in between is used, And the reason we saw that in case 2, the rate of heat transfer was very much less with respect to K1, and that is typically because air has a very less thermal conductivity. Okay, and that's why this configuration is desirable. And we just did a simple analysis. However, so you can do the same analysis by choosing some Hi and H0, which is the heat transfer coefficient for an inner space, and the heat transfer coefficient of the ambient surrounding, and you will end up getting the same qualitative argument so as to why this configuration is desirable. Okay, you can try this out. You can pick appropriate values and try this out at your end. You will again see that this case is only desirable. Okay, it's not so it's just an extension of that. Okay, and then we looked into heat transfer in cylindrical objects and saw how do we write this thermal resistance for conduction. We then looked into a case where there was a conduction resistance for cylinders, plus there was convection at the inner and outer surfaces, and we ended by understanding the concepts of critical radius of insulation, and try to see how the rate of heat transfer in cylindrical objects vary when you increase the thickness of insulation. And it's not always that the thickness of insulation, that adding the thickness of insulation decreases the rate of heat transfer. It is only up to a point where Q only decrease, and after that your rate of heat transfer essentially increases. So the minima of this point, we call it as the critical radius of insulation, and for cylindrical geometry it comes out to be K by H naught. Okay, you can prove this at your end, that for spherical geometry it comes out to be 2K by H naught. This is something that you can do it at your end. And yeah, so this ends the discussion on resistance analysis. I hope you liked it, and we'll meet next week at the same time using the same link. So if you have any doubt, please use the discussion forum. I'll be happy to clarify your doubts. Till then, thank you for watching these videos, and we'll meet in the next week. Thank you very much.